Thanks very much for joining me. You probably already know this. I am very much a definitions guy. I think that we can get a lot of clarity and sort of set the scene for this discussion by starting by just defining things. So maybe briefly, in turn, make sure you guys actually agree for a start. Chip scale. What does that even mean? Lydia?
Yeah, that's I think we all have a different. Well, it's the same thing, but we all maybe think about it differently.
Okay.
So I'm here to talk about quantum error correction mostly. I work for Riverlane, and what we are building is the quantum error correction stack. So imagine something, a box that takes the qubits which are not perfect and turns them into perfect logical qubits. And on top of that, we can build logic. To get to a fault-tolerant quantum computer, we need many, many qubits, which means that we will need a large amount of these boxes. And for us, the best way to keep the consumption down, the cost down, and make sure it works in the best possible way is to tape this process on a chip.
Okay, good start.
This is what I mean about chips.
Go on.
Yeah, let me try. So for us, for Quandela, which is a quantum computing company working on the full stack, chip scale means integrating photonics and elements system nanostructure that allows to create photonic qubits into chips, but also working on how we scale the chips. So it's not only chip scale, but scale chips. And we use two technologies, integrated photonics and semiconductor integrated spins, and we scale these two into different approaches.
Okay. Philipp?
I think I can very much support the point that it really is not about chips itself, right? Most technologies are working with chips in some shape or form. I think it's about from a research scale chip to something that's really manufacturable, because in the end, we've heard also from Maria, right? You need a large system. That means probably on the order of 1 million physical qubits. And in order to do that, you just can't take kind of small research scale chips and hope for the best, that the yield is good and that these will work out. You will need to have kind of an integrated photonics platform that you really have in a fab, ideally in a 300 millimeter fab, with perfect yield, so that you can create hundreds and thousands of chips that you can then network and basically create this digital fault-tolerant quantum computer that's gate-based in order to implement error correction, etc.
Okay, so would it be fair? Is it oversimplifying then? Will we just call it the notion of modularity? If one chip does it well, if one chip is the research level, as you say, then we just want to create chips. You want access to chips that then network together, and it's just a matter of building a bigger and bigger machine, essentially by using more and more chips. Is that a good starting point? Yes. Hold on. There's some reservations there. I'm going to stick with this definition thing.
I think we need to get to something which we term utility scale, so something that's large scale. So the chip itself doesn't matter, sure, as long as you can get to the number of qubits that you need in the end.
Sure, okay, but I guess the question is, if you crack the chip scale question, do you kind of by definition crack the utility scale question, because now you've built the chip that you can just keep stacking more chips next to or on top of?
So I think that brings you a little bit back to why we are talking a lot about photonics today. You really need to think about what are these scaling challenges. Because if you look at the different technologies, specifically photonics has the advantage that connectivity between chips is actually very easy. In our case, we use a dual rail encoding of the qubits. And essentially what we do is we take standard C-band telecom fiber and connect chips. So no transduction needed. And you do see that many of the other technologies now think very hard about how can you actually connect your different chips that you'd also need in those cases without actually incurring high losses, having kind of these additional steps that are not sorted out yet.
Anything to add to that before I get past the dictionary stage of this?
I agree. I just want to add another point.
Please.
Is how many of these chips makes a utility scale machine. So then you can go up to the number of resources, the number of this chip you need, which in the end turns into cost, space, and energy consumption. Because at the end, if we speak about 2030, 2035, 2040, we should not forget that industries are preparing the compliance in the use of cloud infrastructure that also cap a certain amount of energy consumption. So it goes back to the fab, how many of these resources we need to get there. It's important question also that we are very committed in sorting out.
Yeah, I would also second that. So from our point of view, a chip is the only way that we can effectively deliver the quantum error correction stack because of all the things that Niccolo mentioned. Power consumption, the cost, and it's a way to be able to support the QPUs when they scale, and so then we can reach utility.
Okay. Implicit in all of this is getting away from one big machine that has everything inside it, right? In the sense of one collection, if you like, of qubits. And implicit in that, I guess, is the death of the NISQ era. Pause, definitional thing, audience participation thing. Who, before today, or even in the course of today, knows about NISQ? Raise your hand. Enough that we can just throw that around and everybody okay with that? Do we leave too many people behind? Okay. The NISQ era is dead. Jeremy O'Brien triumphantly said, "I told you so," earlier on. Why? For the benefit of the people who know maybe the term, but not like how we ended up having this discussion, why are we not going to get utility out of these smaller machines? One chip instead of two, in your view.
So let's look at it from the application perspective. To solve a problem that's intractable today, we need 1 trillion quantum operations. That means how many times we can run, operations on the QPU before the qubits, they die because of errors. At the moment, the QPUs that we have, because of their size and many other things, we are very far from that. We are on the 100 scale. So I think this, in a way, supports exactly what Jeremy O'Brien said, that if we want to do something useful, and we can define useful in many ways, we need to get to the regime of 1 trillion quantum operations. We cannot achieve that with a NISQ machine.
Anything to add to that? I might be beating a dead horse, by the way, but I also know that this was, as recently as the last meeting here, there was hope for something useful, value generated, money made from NISQ machines.
So I think you can look at this from two sides. The first side is, where do you actually have provable quantum advantage? And that is, starting with Shor, it's all fault-tolerant quantum algorithms, because most of them are deterministic. You can actually mathematically prove that you have a quantum advantage. And all of those basically are, as Maria just said, kind of a million, a billion type gates. So that's one side of the thing. The other is, there has been at some point also reasonable hope, mainly inspired by kind of the first invention of VQE, that you may find something that would actually be just a few hundred gates, a few thousand gates, and could be useful. But the whole field has tried for quite some time now. We still haven't found anything, and there's more and more problems popping up, the Baron-Proteau problem, etc. So the jury's out if you can still find something, but as Jeremy has also talked about, kind of our plan is to have a machine running in 3 years. So the time to actually find something that's not fault tolerant and then valuable is A, very short, and B, it will be very, very constrained to some small thing. And the real promise of quantum computing that we've been talking about 25 years now is coming with fault tolerance, with error correction, because that gives you the full range of applications that we've been proving out also, or start at least proving out with quantum algorithm design.
I would like to rebound on that, and I make my life very hard because I'm in between two experts of error correction and companies that work on this kind of regime. At Quandela, we are not ready to say it's done, And I say that because, as you say, many people have looked into algorithms, into no-go theorem, but a part of this mathematical problem have not been fully explored, we think. So not all the stones have been turned, as we say internally. So we look deep into the mathematical and algorithm complexity theory in a specific encoding that has not been explored, which is not gate-based, but is more prone to photons, which is another paradigm, and work bottom-up, looking at the classical algorithms that can beat an algorithm that comes from this set of complex theory. So we are turning all the stones, and we are positive, scientifically positive, not just business positive, which is our approach. So if we can call NISC dead, we can find another term that maybe can get utility and advantage, most probably also without error correction.
Okay. Okay, I think we've set the bounds here. We know what it is that we're talking about, and we know what the sort of the long-term goal is, I suppose. For the sake of this discussion, fault-tolerant chip scale. Help me understand what the state of the art is and how that falls short of the desired goal. Who wants to start on that nice, easy question? As in, where are things right now? How would you quantify them? In the field more generally, not necessarily in your own companies.
So I can start with at least where PsiQuantum is at right now, and I think we've made large steps, right? So we've basically done the science part of things, the material design, etc. We've almost completed the semiconductor process enablement. So we have all these modules that we've talked about in a 300 millimeter fab now. So we are regularly producing chips. We've produced thousands of wafers and millions of components that we are actually improving by the minute. And as has been discussed already by two speakers today, we've just got a support from the Australian government to effectively build that first system by 2027.
Okay, how are things going so far? What's in the box? And why is it short of that in a few years goal, I suppose?
Essentially, I think that's based on the bet that the company has made 8 years ago. So at a time when everybody was focused on NISC and kind of getting to incrementally larger systems, we have essentially said, like, that's not the path. And it was a very contrarian bet at that point in time. And we've just over that space of time invested hundreds of millions of dollars to make this work. And we've deliberately said we don't produce any kind of intermediate systems. We don't stop in terms of creating something that we believe is not valuable for our partners and customers, because in the end, you can simulate most of that on your laptop anyway. Like, we know you have the provable advantage when you get to that utility scale. And that's what we wanted to achieve. And that's what the company set out to do.
Okay. Go on, Niccolo.
Yeah, on our side, as I was saying, we approach two different paths to get to this large number of qubits, and it's by exploiting integrated photonics and all the components that can be scaled, manufactured, and pushed to the limit via standard foundries. But there is an approach that we take, which is on the generating entanglement and generating photon, which is not through these components, which are available in foundries, but are based on a technology that we exploit, semiconductor, quantum dots, and spin. That is what is part of our scientific core, 20-year research that we spin off in Quandela. So we are scaling now this because it doesn't exist in the industrial world. So we took it out of laboratory, we commercialized it, and we launched the past month, we announced it today actually, a first pilot line that will leverage all the industrial processes to bring this into industrialization at the large scale. In number, it means that if we were able to fabricate 200 devices in the past year, we are now moving to the thousands. And when the full machine, the full pilot line will get completed, we're now 90%, we will get to 10,000 devices a year. And now we use one device to manipulate tens of photons, tens of qubits. So that's the scaling we are bringing up, reducing the resources, pushing on a technology in the industrial way, industrial processes, looking at automatization with what external foundries, large foundry can do best, which is integrated photonics.
Right. And Maria, your view here, extra valuable because you are kind of platform agnostic, I guess.
Yes.
So, slightly more mile-high view then. What is the state of the art?
Yeah, so from our side, again, we are focusing on the quantum error correction. So the way our system works is based on redundancy. So we have the qubits on the chip. We have to encode information in multiple qubits. And then we have to poke some of them to see if an error has occurred. So this information has to be fed into a decoder. The decoder has to decide where and if errors have occurred, and then issue corrective measures, again, back to the qubits. This is a cycle that needs to happen very quickly. So the stringent requirements come from superconducting qubits, and this has to happen within 1 microsecond. If it doesn't, the errors will accumulate, and this backlog will occur, and the quantum computer will come to a halt. So at this point, we have solved this problem. We have a decoder that works in these very stringent requirements. And we are now focused on expanding that and improving it. This means working with decoders that are faster, that are more accurate. And we also have to think about the system scaling. We are now working with the number of qubits that are available, but eventually they will have to scale to millions and even more. And then the whole system will be even more complicated. We will have many decoders, they will have to talk to each other, and there will be a very complicated orchestration of the data that, again, will need to happen very, very quickly. The buzzword in Riverlane is QOPs, quantum operations, how many we can get. And for us, the next big milestone is to deliver a quantum error correction stack that can support 1 million quantum operations. Because at this point, we will be able to start doing something that we cannot simulate classically.
Right. I mean, along the way there, you said, well, we have to poke a few of them.
Yes.
The latent engineer in me wants to know exactly where we are with regard to all of the other stuff. It's sort of sexy to talk about the qubits and the qubit instantiation and the how many you can get in a chip at a fab, what have you. But you still need tons of control electronics, cooling, all sorts of things that are just as much an engineering challenge as the sort of the more naughty physics end of it, right?
Totally.
Well, I would say that at this point, the physics is well understood, and it's an engineering problem. So we work across the qubit types with all qubit modalities, and we believe that they can all get to the million quantum operations in the next years. It's not a physics problem anymore. I mean, what do you guys think?
I think that physics can help to optimize also the architecture, not only to build faster, so to reduce the engineering problems, but also to use smarter ways to encode qubits, to apply error correction, and bring the threshold down, which is helpful for the engineering, but also on the theoretical side. So there are no maybe scientific roadblocks, but also science must be pushed to the limit to bring this regime closer.
Absolutely.
Yeah, I'd like to build on what you say, and I agree, right? Basically, everybody can build good qubits now. The point is really, how do you get them to scale? And if you not have 10, but 1 million, do they still work at the same level and at the same quality? And that's just not the case for every technology. And that's a bit why we are talking about photonics here, because we've talked about the manufacturing element of it. We've talked about the connectivity element. But there's also control electronics, right? So essentially, we bump bond our control electronics on top of the photonics chips. That gives you a very short latencies, makes it very easy to do. We also don't have the problem kind of that you are at millikelvin temperatures, and therefore can basically work with industrially available cooling facilities. It's a lot of cooling power needed, but it's not something that you need to invent from scratch and really hope for new innovation, but it's something you can order.
I guess what I was sort of digging at with all of that was to find out what are the remaining stumbling blocks. What are the things that are the hurdles you still know you have to get through? What are the things that keep you awake at night at this stage? Who wants that one?
I can take it, because what I think is really one point, like I think we have a roadmap towards the hardware now, but I think what the field doesn't do enough is actually looking at the algorithm development for fault tolerance. There's probably 100 people out there who are really good at doing fault tolerant algorithm design. We invested as a company quite a lot of money and quite a lot of people in actually getting to a software suite with which you can efficiently program something like this and get to a point where you can optimize these things. We see orders of magnitude improvement on existing algorithms kind of every year. And it just needs more people looking at how can you improve these algorithms and honestly apply them to problems that are really commercially useful. When I'm looking at the field, I'm always surprised seeing there's a couple of standard benchmark type problems out there like Maragkou or the RSA problem, but like the way they are framed, they will not help, right? We need to get to a point, and that's something that we have done as a company. If you have a perspective on having a machine in 3 years, you actually need to make sure that there's algorithms to run on that machine that will produce something commercially useful. And that is something where the field is really lacking right now, and it needs much more concerted investment into fault tolerance and making that step also from NISC, where still a lot of the activity is happening, to fault tolerant algorithm design in order to bridge that gap.
I agree totally. That's why on the algorithm side, we have not yet prepared the algorithm on the fault tolerance, but we start with the same idea that we should not just pick up what is there, but we have to develop something from what the machines can actually provide best. So try to get through a regime or application that we can explore after we know that a certain algorithm can scale, it cannot be beaten by any classical machine now and never. What keeps us awake at night still is also the engineering part. So if we are in photonics, what keeps us awake is not to lose any photons. Every photon counts. So that's what keeps us awake now.
Right, fair enough. For you?
Yeah, I would agree with all of this. So our job is to make sure that we reduce the overhead of quantum error correction. So the amount of extra qubits that we need is as low as possible. This will make your life easier. But then the problems on the QPU side remain. How the QPUs will scale, the qubits, and all the components around them. Like you said, the control system, the fridges when needed, the lasers, all of that. And I agree, the connection with the end users is very, very important. Finding algorithms that are commercially relevant, that can solve problems that are intractable today, it would be nice if, more people are into that. I mean, building a quantum computer is very, very hard. We don't do it just because it's fun. We do it because we think we can solve something that will be of real use to everyone. Everything it all has to come together. Yeah.
It's sort of interesting, though, that one of the bottlenecks here is in the talent pipeline, if you like, is the algorithm engineers. Look forward to a future Economist Impact Quantum Algorithms Conference, I suppose. That seems to be, because we've heard also today that the smart way to do this is to have everything ready at the right time, right? Once the car is ready, the driver is ready, the mechanics are ready, vice versa, all of that. Like, to not know exactly where the high commercial value algorithms are at this stage, talking about, means of cooling and so on. I mean, I wouldn't say cart before horse, but there's a certain parallelism that seems absent here. Do you guys feel that? You build the machine and you can't make it go fast yet.
So I would say from our side, so from the technical side, we are doing the best we can, and we do hit the milestones that we've promised. So technically, the field is moving in the right way, and I dare say that some of the milestones are hit sooner than we thought some time ago. The resources are coming down, the QPUs are scaling, so everything we are doing the best we can, and it's working very well. What maybe we can work better is working with the end users now, earlier, because it will not, I think, so from our point of view, these machines will be extraordinary. And if we want them to have an impact, we have to rethink the whole workflow of an industry. It will not be as simple as, oh, this is my workflow. I'm going to take this little bit and I'm going to run it on a quantum computer and it will go 3 times faster and it will be great. We have the possibility to really think that from scratch and get even more out of a quantum computer. Everything has been made classically. All this workflow has been thought from a classical point of view. Now we have a new machine. Let's push the boundaries as much as we can. And to do that, we have to start working with the end users as soon as possible. So the algorithms are the correct ones, so they are focused on problems that have value to the various industries. We don't have chemistry or pharmaceutical experience in-house. We expect the pharma companies, the various industries to come to us and tell us, this is the problem that I have. Let's work together and see how we can really use quantum computers.
Yeah, we have the same approach. So we build machines, we work on this hardcore mathematical description of the algorithm we want to implement, but we also work in building up a community. We want to make these machines, the initial ones, to be used, to be, as Maria is saying, integrated, even if the return on investment is not yet there, but we have to be prepared. And I think also users have to be prepared internally to get this transformation, this quantum transformation, follow up internally. And it applies today with some kind of service or cloud access. And that's what we work on since the beginning. So we open it, our open cloud access at the end of 2022. It was the first in Europe. And we keep increasing the community and we keep pushing the services and the stack on the middleware and software to get this integration easier on the user side.
It all makes great sense, right? But it seems a little bit sort of abstract, I suppose. Thinking we've talked about a community of people, you've talked about the end users, what have you. Some of those people are here in the room. Concrete things we can tell them they should be doing, or maybe how to think about this transition to chip scale and the end of the NISC era, which went by, I think, sort of kind of unheralded, really. We talked for many years, and then now it's kind of behind us. Now we're talking chip scale. If you are a business leader, and you are thinking, not sure if my industry lends itself to this, or I don't know how to prepare myself for this. From the inside of this, as you believe you are certainly on a track towards the real utility scale thing, not quantum advantage, what would you say to those business leaders? Here's what you should do, here's how you should think about it, here is how not to lose sleep.
So I think...
I would just say, come talk to us. Talk more to the people who are building the quantum computers or various aspects of the stack and help us understand where we can really help you so we can all work together. That's what I would say.
So I think I've seen way too much hype in the system and way too many many discussions left and right. But I think given that we now have line of sight to a system, at some point you at least need to make up your mind and create a perspective in what quantum computing will mean for you. Because on the fault tolerance side of things, you can actually do comparisons. You can look at quantum speedup, and not only on the asymptotic side of things, you can make concrete instantiations of an algorithm, so you know exactly kind of what would the runtime be on a system, and really figure out if there is utility, if there's value for your company. And you've heard it earlier, I think Mr. Bennett was also talking about that. Like, there won't be a ton of systems out there. And we've also talked about scarcity of talent. So if you really want to play in this field, you need to sort this out sooner rather than later. The decision can be no. But if you want to play, there's a limited amount of capacity that you can actually address. And there's a limited amount of talent that can create your fault-tolerant algorithms. And if you want to play, you better decide soon.
Ominous.
I will add just a final thing. I totally agree. For us, the first point is be clear of what is quantum computing today, which is fighting against hype, be honest on where we are, but at the same time, be rigorous and show where we are going. So open up the path to the user so the user can project in 2, 3, 5 years and start to prepare this accordingly to the evolution of the field and what the company, what we can provide to them. Because that's clear for us, but we have to make it clear also to who will use these machines.
Right. Clarity and hype-free, that's why we're all here, isn't it? Right, Maria, Niccolo, Philipp, thank you very much for your time. Let's give them a hand.